Let's continue with our discussion of the wall of physics. In the last lecture, we said that the Standard Model plus general relativity can explain almost all phenomena in the world. I say almost because they cannot explain absolutely everything. They fail to account for dark matter and dark energy. These may hold the key to a major shift in our worldview. Let's start with dark matter, which is actually an old problem. As early as 1933, astronomer Fritz Zwicky noticed that galaxies on the outskirts of the Coma cluster seemed to be moving too fast. A galaxy cluster is a collection of many galaxies bound together, and they orbit the cluster's center of mass under the influence of gravity. Much like the Earth orbits the Sun, or like swinging a ball tied to a string. The faster the ball spins, the greater the force you need to pull the string. So if galaxies on the outskirts are moving too fast, that means the cluster must be generating a much stronger gravitational pull. But if you count the galaxies inside the cluster and estimate their total mass, you find it's nowhere near enough to produce that much gravity. Zwicky concluded there must be some additional, invisible matter there. He called it dark matter. Zwicky's measurements weren't precise, and people paid little attention. But in the 1970s, astronomers discovered that this effect wasn't limited to clusters. Even stars in the outer regions of individual galaxies were orbiting too fast. Then in the 1980s and 1990s, new evidence emerged from gravitational lensing. According to general relativity, light bends in a gravitational field, producing a lens-like magnification effect. Observations showed that gravitational lensing in some clusters was far stronger than could be explained by the mass of visible matter alone. In the image, the blue halos represent dark matter distributions inferred from gravitational lensing. All of this evidence pointed to one conclusion. Galaxies are filled with massive amounts of dark matter. By the 2000s, physicists realized dark matter is crucial to the universe's very existence. In the early universe, without dark matter, the gravity from normal matter would have been too weak to form stars and galaxies in time. From this, we can further deduce that, whatever particles make up dark matter, they must move far slower than the speed of light. Something viscous, in a sense. In particle physics terms, slow motion means low temperature, so we also call it cold dark matter. Dark energy is even stranger. We know very clearly that the universe has an origin. The Big Bang. Ever since, space has been expanding. General relativity predicted it, astronomy has confirmed it, and we've even found the Big Bang's afterglow. The cosmic microwave background radiation, beyond all doubt. Logically, the rate of expansion should be slowing down over time, because of gravity. It's like throwing a ball into the air. Even if the ball's initial speed is enough to escape, gravity will always slow it down, right? Physicists once imagined that gravity might eventually stop the expansion, or even reverse it into contraction. But in 1998, two independent research teams, studying distant supernovae, made a shocking discovery. The expansion of the universe is not slowing down. It's accelerating. We have no idea what mysterious energy is driving this acceleration, so we call it dark energy. So what are dark matter and dark energy? Your first thought might be, maybe general relativity is wrong. Maybe our understanding of gravity is too simplistic. Perhaps gravity is stronger on galactic scales than we think, and on cosmic scales it turns into some kind of universal repulsion, explaining both dark matter and dark energy. Trust me. Physicists have thought of that. Many have proposed alternative versions of general relativity, but all have been ruled out. One interesting fact. Dark matter isn't everywhere. Some galaxies seem to have none at all. You can't seriously claim that different galaxies obey different laws of gravity. General relativity is fine. You must include dark matter and dark energy to explain the universe's evolution. Around 2000, physicists proposed a standard model of cosmology, called the Lambda CDM model, where lambda is the cosmological constant representing dark energy, and CDM is cold dark matter. This model says that ordinary matter, the stuff we can observe, makes up just 5% of the universe's total energy. Cold dark matter accounts for 27%, and dark energy for the remaining 68%. The Lambda CDM model successfully describes the universe's evolution from the Big Bang to the present, matching observations well. According to it, our universe is 13.78 billion years old. I was reminded to write this article, because I once thought the Lambda CDM model might be overturned. In 2021, the US launched the James Webb Space Telescope. Almost immediately, it made unexpected discoveries. Most strikingly, it observed several extremely massive galaxies, more than 13 billion light-years away. Remember, because the speed of light is finite, the farther away we look, the earlier in time we see. Those galaxies existed when the universe was only about 300 to 400 million years old, or even younger. But according to the Lambda CDM model, the universe back then was too young to have formed such large galaxies. This was thrilling. Such mismatches often lead to scientific breakthroughs, perhaps revealing deeper secrets. Could it mean the standard model of cosmology is wrong? In 2023, someone proposed that the true age of the universe might be not 13.78 billion years, but 26.7 billion. If true, our worldview would be upended. But it was probably a false alarm. In 2024, researchers at St. Mary's University in Canada studied more nearby galaxies and found that they weren't unusually massive at all. Everything looked normal. Early observations may have been flawed, or the light from multiple galaxies may have blended together. The Lambda CDM model still stands. Webb has indeed made new discoveries, but so far they have only refined our understanding of the early universe. They have not overturned the model. So the worldview of physics remains stable. I sometimes wonder, if Feynman were to travel to our time, what would he say about the development of physics? Richard Feynman was perhaps the last physicist to become world-famous for his distinctive personality. He did brilliantly creative work, and his physical intuition, humor, and teaching style are still celebrated by students today. Since Feynman's time, physics has increasingly shifted toward large-scale collaborations. Research is more industrialized, with fewer chances for individual flair. Feynman died in 1988. By then, the Standard Model was long established, he knew about dark matter, and he had even envisioned quantum computers. If he saw today's progress in quantum computing, he would be pleased. But the thing that would truly amaze him would be AI. He could never have imagined large language models being this capable, or that we might be on the verge of AGI and ASI. As for physics, though, Feynman might shake his head. You detected gravitational waves? Amazing. But that's just confirming general relativity. I worked out the reality of gravitational wave energy back in the 1950s. The LHC finally found the Higgs boson? Great, so the Standard Model holds up. We got that one right back in my day. Roger Penrose got the 2020 Nobel for black hole work. But Oppenheimer proposed black holes in 1939, and my advisor Wheeler named them. You know what I admire most about Penrose? That he lived long enough. If Hawking had lived a bit longer, he'd have gotten one too, but either way, it's all just confirming what we already suspected. The only thing that would truly shock Feynman is that the universe's expansion is accelerating. But apart from stating that fact, we still know almost nothing about why. And if he heard how much manpower and money, tens of billions of dollars, modern physics invests in giant experiments, he might quote a popular AI meme, "Physics has no scaling law." Thank goodness, we don't have an Nvidia of physics, or the stock would have tanked. The Standard Model, general relativity, and the Lambda CDM model together form physics' latest explanation of the world. And this, latest version, hasn't been updated in many years. These three theories can explain every physical phenomenon you can think of, but no one is satisfied. Too many things feel unnatural and in need of deeper explanation. For instance, the Standard Model describes the small-scale world, full of uncertainty, where all forces are mediated by particle interactions. By contrast, general relativity describes the large-scale world, deterministic and geometric. Gravity is the curvature of space. The two are fundamentally incompatible. In black holes and at the universe's origin, you must deal with strong gravity at tiny scales, so is gravity deterministic or uncertain? Is it a particle or a curvature? Physicists have long tried to unify the Standard Model with general relativity, inventing elegant theories like string theory and loop quantum gravity. But decades on, these remain mathematical exercises with no experimental evidence. Feynman would not be surprised. He was skeptical from the start. Then there's the issue of the Standard Model's 19 free parameters. Things like the mass of the down quark, the strength of the electromagnetic interaction, etc. These are not dictated by theory. They come from experiment. Change them even slightly, and our universe would be unrecognizable, likely incapable of supporting life. Where do these parameters come from? Did some god fine-tune them so life could exist? And what exactly are dark matter and dark energy? They too are awkwardly inserted into our models, with no known origin. The Standard Model and Lambda CDM work beautifully, but they're not elegant. They feel cobbled together. If these are the universe's blueprints, we still want to know the deeper design principles behind them. And then there's quantum mechanics. Is quantum uncertainty a fundamental feature of reality, or just a limit of our knowledge? What is the mechanism behind quantum entanglement? These questions have haunted us for a century. Right before our eyes, physics has run into a wall. The wall is clearly artificial, full of chisel marks. We know there must be something beyond it. But for decades, we haven't been able to break through. Some say AI might help, but I'm not so sure. If our problem were just that, physicists aren't smart enough, AI could help. But our problem now seems to be that we lack more powerful experimental tools. For example, testing string theory might require a particle collider the size of the moon. Humanity won't build such a thing anytime soon. So we look to the sky. The universe is the poor man's laboratory. But no matter how powerful our telescopes get, they may never let us see back to the exact moment of the universe's birth. Which means we might never know what lies beyond the wall. The universe has no obligation to be understood. Still, as the saying goes, every wall is a door. There is hope. The good news is that we've found at least 2 cracks in the wall. Both are related to neutrinos. Neutrinos are fundamental particles in the Standard Model. They carry no electric charge, and you never feel them. They only show up during nuclear decay. The Standard Model says neutrinos should have exactly 0 mass. But experiments have shown they have a tiny, non-zero mass. Where does it come from? Also, in a perfectly symmetrical universe, every particle of matter would be paired with an antimatter particle, and they'd annihilate each other, leaving no matter at all. So why does our universe contain so much matter? This asymmetry is linked to a kind of symmetry breaking involving neutrinos, but the Standard Model's calculations can't account for the observed difference. These 2 facts show that the Standard Model is not absolutely correct. The wall has weaknesses. Whoever breaks through them, whoever solves any of the problems I've mentioned here, will have their name forever listed alongside the great heroes of physics history. That's it for today's content. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.